So, the next topic that we are going to look at in the braking analysis is the analysis of wheel lockup. So, when we are discussing anti-lock brake systems, we looked at the effect of front wheel lock and rear wheel lock, right, if you take a single unit vehicle like a passenger car. So, if the front wheels are steered and front wheels lock up, we lose the ability to steer. However, if the rear wheels lock and if there is a significant lateral disturbance, what happens? The vehicle may spin out of control. So, we lose directional stability. So, for that reason we essentially discuss that the sequence of locking becomes important, right. Of course, ideally, I am repeating myself, in an ideal scenario wheel lockup should never happen, but if it were to happen, the sequence of wheel lock becomes important, because we may want the front wheel to lock before the rear wheels, since front wheel locks at least can be readily more detectable by an experienced driver than a rear wheel lock, and the driver can correct it, right. So, that is where the analysis of wheel lockup becomes extremely critical. So, what is this analysis going to deal with? Okay, we shall analyze the conditions under which the front wheels and rear wheels will lock. So, the motivation behind this analysis is because the sequence of wheel lock matters, right. So, that is why that is what we want to essentially look at. So, in this regard we are going to make some basic assumptions. So, what we are going to do is the following. We shall consider only braking force and rolling resistance, okay. We are going to neglect the other resistances like grade resistance and aerodynamic drag and drawbar pull and so on, right. One can include them, but then like for the sake of simplicity, like we consider only braking force. In fact, if you look at braking, the magnitude of the braking force is much above all the other resistances, right. But let us say like we consider only braking force and rolling resistance in this particular analysis, and we shall consider that the BFD which is given to us is KBF to KBR, right. So, we are already given a vehicle with a brake system designed and installed in it, which gives us a brake force distribution of KBF to KBR. Let us say we have a 60-40 BFD, that means KBF is 0.6, KBR is 0.4, that has been given to us. So, then what do we do with this? So, under these assumptions, I am just going to write the summary of equations. You can go back and check these equations as an exercise, because we just derived those equations, right. So, we consider the same free body diagram with under these assumptions, right. In the presence of only braking and rolling resistance, we neglect the other resistance. Thus, the governing equations become the following, right. We will get W by GA to be equal to FBF plus FBR plus RR. This is nothing but FB plus FRW, okay. We already know about this, right. So, why? Because this is the total braking force FB, this is nothing but FR times W, right. That is the rolling resistance force, okay. Now, the expressions for WF and WR can be once again calculated by taking moments and taking cos theta as to be almost 1, right, and making the same assumptions, right. So, the expressions for WF and WR become, in this particular case, WF will be W by L L2, oh sorry, let me write it carefully. We will have W by L2 plus W by G A H by L, which can be, it is just the same equation written under this condition. This is going to become W by L, L2 plus A by G times H. Okay, so that is what it is. Alright. So, this is for the front. How did we get this? Once again from the same expressions, right, what we derived, right. So, nothing more than that. Okay. So, WR is going to be W L1 by L minus W by G A H by L. So, this is going to be W by L L1 minus A by G times H. So, this is for the normal load on the rear. So, once again we can see the effect of dynamic load transfer, right. See, by the way, one important point that we should observe, particularly with respect to dynamic load transfer, please note that the dynamic load transfer is dependent on the CG height, right, because what is the dynamic load transfer in this case? It is FB plus the magnitude, it is FRW times H by L, right. FRW is going to be small when compared to the braking force, okay. So, the CG height H influences it. You can immediately see that the wheelbase L also plays a role, and so is the braking force or level of braking, right. So, depends on whether we are doing mild braking or panic braking where we slam the brake pedal and so on, right, depends, affects the dynamic load transfer, okay, during braking. So, if we come down, we will see that effect is felt here by means of deceleration. Still you see that the height of the CG and wheelbase plays a role, but the level of braking force is reflected through the deceleration A by G, the normalized longitudinal deceleration, okay. So, there we wrote it as FB, here we are writing it as A by G, that is it, okay. So, the equivalent representation, right. So, yeah. Okay. So, now given the brake force or given the BFD of KBF is to KBR, the brake forces on the front and rear wheels are the following, okay. So, what will happen in the front? You will get FBF to be equal to KBF times FB. How do we get this? Because that is the definition of KBF, right. KBF was FBF by FB. So, I am just writing FBF as KBF times FB. So, now what we do is that we substitute for FB. Where do I substitute for FB? From this equation. So, I will get KBF W by G A minus FRW. How did I get this equation? From here, right? I use this equation, right. So, I substitute for the net braking force. So, this is nothing but KBF W A by G minus FR. Right? Okay. Similarly, FBR is going to be equal to KBR times FB. KBR is nothing but 1 minus KBF, right, because KBF and KBR sum to 1. So, I can write KBR to be 1 minus KBF times FB, the expression is still the same, we will have W by GA minus FRW. So, here I will get 1 minus KBF W times A by G minus FR. Okay. So, this will be the expressions for the brake force on the front and the rear, right. So, now the front wheels will tend to lock. So, if you discuss our discussion on the traction at the tire rod interface, the maximum longitudinal traction is mu p times W at that tire rod interface, right. So, anytime the applied braking force exceeds that value of mu p times W, we are going to have problems, right. So, that is what we discussed. So, the front wheels will tend to lock when FBF becomes greater than or equal to mu p times WF, right, is not it? WF is the load at normal load at the front tire rod interface, mu p is the corresponding peak friction coefficient, mu p times WF is the maximum traction force available at that tire rod interface. So, if the front brake force exceeds this limit, there may be a tendency to lock, because the slip may go beyond the value corresponding to the peak mu p, and then it may go towards lock. So, if you recall the friction ellipse, right. So, if we are exceeding this, we are going outside that ellipse, right, beyond the boundary of that ellipse, right. So, that is what is going to happen. So, in the limit what happens, we can have mu p to be equal to this FBF, just to calculate the expressions, FBF to be equal to mu p times WF. This will just help us in calculating what is the deceleration after which front wheels will tend to lock. Okay, we are going to observe that shortly. So, let us look at the limiting case. So, FBF is going to be equal to KBF W A by G minus FR, right. How did we get this? From the above expression, and then mu p times WF. So, if we go up, we already have the expression for WF, right. So, that is going to be W by L, L2 plus A by G H. So, here we can see that W and W cancel off. So, now we can see that there is an A by G on the left hand side, A by G on the right hand side. We just do some simple algebra and then find an expression for A by G. So, what we will get is the following. So, if I take A by G common, I am going to get KBFL minus mu P times H, that is going to be equal to mu P L2 plus KBF FRL, right. I am just rearranging the terms. So, then what we will have is that, like, we will have A by G is equal to mu P L2 plus KBF FRL divided by KBFL minus mu P H, alright. So, this we will put a subscript F, and what is this expression give me? It is the longitudinal deceleration, this is the limiting longitudinal deceleration of the vehicle, right, beyond which front wheels would tend to lock. Okay, so that is the meaning of this particular expression. Okay, the physical interpretation of this is that this A by G subscript F is the vehicle longitudinal deceleration beyond which the front wheels will tend to lock. Okay, so that is why I wrote subscript F in a different color, because this is not what to say longitudinal deceleration of the front wheels. No, this is the longitudinal, A is the longitudinal deceleration of the vehicle, right. So, this gives us a limiting value beyond which the front wheels will tend to lock. So, we can do a similar analysis for the rear wheels, right. So, similarly the rear wheels will tend to lock when FBR is greater than or equal to mu P times WR. So, in the limit what happens, FBR becomes equal to mu P times WR, right. So, we apply the same process, we have 1 minus kbf W A by G minus Fr, that is our FBR, and on the right hand side we will get mu P W by L L1 minus A by G H. So, W and W once again cancel, you can see that there is an A by G on the left and the right hand side. So, this once again like if we rearrange and simplify, what we are going to get is that we are going to get an expression for A by G, that intermediate step I leave it as a simple exercise, right. So, this expression will now be mu P L1 plus 1 minus kbf FRL divided by 1 minus kbf L plus mu P H. Okay. So, this let us put a subscript R. So, this is the once again the longitudinal deceleration of the vehicle beyond which rear wheels would tend to lock. Okay. So, that is the meaning of this expression, right. So, now let us say like A by G subscript F is let us say 0.7, A by G subscript R is 0.8. So, during the braking process, which wheel do you think will lock first? Front wheel, right, because the vehicle deceleration has to cross 0.7, only then it will go to 0.8, right. So, consequently, we can immediately observe that the front wheels would tend to lock before the rear wheels. If A by G F is less than A by G R. Okay. So, that is the first point. Similarly, the rear wheels would tend to lock before the front wheels if it is the other way around, A by G R is less than A by G F. Okay. So, we can see that by doing this analysis like we would be able to get an idea as to how like one can determine the sequence of wheel lock under different operation conditions, right. So, that is the main impact of this analysis. Thus, this analysis helps us in understanding the sequence of wheel lockup. Under different operating conditions, because why? Because you can see that it is a function of KBF, brake force distribution, it is a function of mu, it is a function of CG and so on, right. So, under various operating conditions. Okay. So, that is the at least impact of this analysis. Okay. So, from this one parameter that is defined based on this understanding is what is called as braking efficiency. Okay. So, what is the definition of braking efficiency? It is the ratio. So, if you look at it, so if continuing upon the previous discussion, even if you look at the normalized deceleration that you can expect, like if you are looking at this expression, right. So, if you look at W by G A, okay, and you look at the limiting case, FB is going to be mu P times W plus FRW, right. So, this is the maximum, right, in the limit. So, theoretically what we are going to get is that the A by G max is going to be equal to mu P plus FR. Do you agree? Because if I cancel off W, right. So, that is if you look at this governing equation, neglecting all the other resistances, so we can observe that I will get the maximum deceleration when FB is maximum. When is FB maximum? The maximum brake force is going to be mu P times W, alright, that is the maximum limit of the braking force, right, based on the interface, tire road interface conditions, right. So, now we can eventually see that the maximum normalized vehicle longitudinal deceleration from this, what to say, simple analysis is going to be mu P plus Fr, please remember that, okay. So, that is what we are going to use in this definition of braking efficiency. So, it is the ratio of the maximum deceleration, of course, in terms of A by G, okay, normalized by G, okay, achieved prior to lockup of either front or rear wheels. To the sum of mu P and Fr. So, what is the expression for this braking efficiency? So, eta B I can rewrite it as minimum of A by G F comma A by G R, right, because say I need to take the minimum, right, is it not, because as per the definition it is the vehicle deceleration achievable prior to lockup of any wheel on the vehicle. So, I need to take the minimum of A by G F and A by G R and divide it by mu P plus F R, right. So, when I have very effective brake force distribution, you will see that A by G F and A by G R will be almost equal and this braking efficiency will almost tend to 100%. So, if you have perfect brake force distribution, right, between the front and the rear, you will achieve the best possible braking. But unfortunately, as we just discussed, brake force distribution is dependent on so many conditions, right, the vehicle CG location, the tire road friction levels and so on. So, this quantity also keeps on changing, right. So, that is why like active brake control becomes pretty interesting to do, right. Okay. So, I think this is a good place to stop for today's class, okay. So, we will continue in the next class. Thank you.